Hi everyone, I'm Zhihao, and today I'm really glad to be here to talk about my recent work on the 3D object detections. To start with, I'd like to talk about the background of the 3D object detections. For the 3D object detections, it is very similar as the 2D object detections. The model consumes the raw point cloud data as the input and outputs the 3D object bounding box location. In general, the 3D object detections could be categorized into three types. According to the model type, there are single-stage and two-stage model structures. And for the data consumption types, the model can take the raw point cloud or image data as input. Last but not the least, for the LiDAR-only method, the point cloud data structures can be formed by two types, which are point-based sparse and or the grid-based dense. There are some difficulties and challenges according to the 3D point cloud data structures. For the point-based point cloud, it has highly unordered data structures. And also for the two-stage models, the amount of points is prohibitively huge, where the high redundancy exists in the point-based generated anchors. And for the voxel-based point cloud, the voxels are extracted from the evenly partitioned point cloud space within each space, and the features extraction algorithms merge the multiple downsampled points to a fixed length vectors, which result in information loss and lacking the integrity of the points relationship. Point RCN and PointNet are the two methods to achieve the 3D object detection tasks. For the point RCN, it is a two-stage models. In the first stage, it takes the raw point cloud as input and predicts the proposals on each point. And in the second stage, it utilizes the ROI poolings to pull the point-wide features from each proposals and followed by the fully connected layers to predict the final result. For the voxel net, it formed the point cloud into a voxel space and followed the 3D convolutions to extract the high-level features and project the 3D features onto a 2D feature maps to predict the final results. So our ideas is to merge the point-wise and voxel-wise data structures together to extract the proposals. So in the first stage, we take the raw point cloud data as the input, followed by two lightweight voxel dense and point sparse networks to extract the proposals. Then the proposals in the real sense can be seen on the right side. The red box indicates the point-wise sparse proposals, and the blue box indicates the dense proposals. So in the second stage, we merge the dense and sparse proposals by the Euclidean distance, and to pull the point-wise and voxel-dense features from each proposals to concatenate high-level features which contains a final classification and regression information. Here is the detail of the ROI deep fusion layers. We extracted the voxel features with different respective fields to form a course to find the voxel-wise features. And also we're using a lightweight point net to extract the point-wise features, which preserve the original 3D space point information. Afterwards, we concat the voxel dense features and the point-wise features together to reach the proposal-aware fusion layers. For the loss functions, we followed the most object detection models use the focal loss as a classification loss and the smooth L1 as a regression loss. The main difference is that we got a point-wise sparse and voxel dense branches, which contains two loss separately, We simply sum the two losses to achieve the combination loss. We're using the two hyperparameters alpha1 and alpha2 to tuning the loss balances, which is not perfect in our works. So for future work, we probably do more works on the reduce the complexities of the joint loss. Our performance outperformed many state-of-art models, especially in the car and pedestrian detections under the easy mode. And also we compared the recall rate in the first stage with other methods, which increased by 3 and 6%. And we also compared our own models. We did the experiment on voxel and point fusion layers, which gives us the result. The joint pooling method increased the performance by 3 to 4%. Here is the demonstrations of our model. We inference our models on the 2080 Ti GPU, which can reach 15 frames per second. Yeah, that's it. Thanks for the listening.